Okay, welcome to this computer science course. The first chapter is information representation. And the learning objectives are these. By the end of this chapter, you should be able to show understanding of binary magnitudes and the difference between binary prefixes and decimal prefixes. That is, a binary prefix kibibytes and decimal prefixes kilobytes. Just a taste of what you're going to learn. Prefix is something in front. Suffix is the one that is afterwards. So prefix, kilograms, something like that, kilo, right? That is decimal. Kibi is a new one that you're going to learn. That's a binary prefix. And there you get 2 to the power instead of 10 to the power, right? The column values. So understanding of the basis of different number systems. So there are different number systems. What we use is the decimal, commonly called decimal system. In the Cambridge, for the Cambridge exams, for that syllabus, they are calling it denary. Show understanding of the basis of different number systems, how they are based, right? Basis. What's the base? Different bases for different systems. Perform binary addition and subtraction. Normally, you know decimal, 10 plus 15, you know how to add. But here, binary, also you're going to learn addition and subtraction. Describe practical applications where binary coded decimal, as a new thing, BCD and hexadecimal are used. So understanding of and be able to represent character data in its internal binary form, depending on the character set used. That means when you type a letter A, the letter A in that form known to us will not go into the computer. A different binary character, binary code rather, in machine code for A, and for B, another one, likewise. For capital A, one code, for simple A, another code. So understanding of data for a bitmapped image are encoded. The images have to be encoded, like when you save in a file, create and save a file. They have to be coded. So how are images encoded? There are 2 types of images. Perform calculations to estimate the file. How do you calculate the file size? After creating a bitmap and you save it, there is a particular size for that file, depending on the image. How do you calculate that? We'll learn that. Show understanding of the effects of changing elements of a bitmap image on the image quality and file size. How do you make changes in the elements of a bitmap, and how the image quality and the file size, they are affected. And also you will understand how data for a vector graphic are encoded. So that is the other type of graphic. First bitmap, then vector. Justify the use of a bitmap image or a vector graphic for a given task. What does that mean? If you select a bitmap, you can select any, either bitmap or vector graphic, but you have to justify, means you have to give reasons for using bitmap in preference to vector. Or if you're using vector, then why you are using vector graphic. Show understanding of how sound is represented and encoded. So similar to the images, how is the sound encoded? And we'll understand the impact of changing the sampling rate and resolution. So those 2 are coming under sound encoding, sampling and resolution. So understanding of the need for and examples of the use of compression. What is the need for compression? Compression is making small. File compression is making a file smaller in size. And why do you need to do that? And also give examples. Lossy and lossless compression, two of the methods, and justify the use of a method in a given situation. Again, why you use a lossy or lossless? The reason. And all finally, you will understand how a text file, bitmap image, vector graphic, and sound file can be compressed. Firstly, we start with number systems. The denary numbers, so what we know as decimal, called denary, the Cambridge syllabus. Denary. Base is 10. So I have given a summary of all the nodes. Base 10. That means 10 digits. If the base is 10, the same number of digits will be there. And we know them as 0 to 9. Then once you with one, you start with one digit or one column, this column, you can go up to only 9. You're using only one. Only 9, from 0 to 9. So you can imagine how people would have started counting humans using their fingers. So only 10 is possible, no? That's why digit has a meaning of like a finger also, right? Then there's 10. So the first column or the first time you use the finger, you can go only up to 0 to 9 and the 10 fingers are finished. Then you need columns, more columns. So when you go on to the other one, 10 to the power 1, which has a value of 10, higher value than this. Then the third column is 10 to the power 2, which is hundreds, higher than this. So at this point, you will see, I will show you a video which will tell you how humans would have most probably started using the decimal counting system. Let's have a look at this video, birth of the decimal counting system. This will be your course page, so you will also be able to look at it or watch either this video or any video or lesson or assignments given in this course page. You will be able to watch and follow any number of times as you want. So let's have a look at this.
I am going to tell you how and why humans settled for the decimal counting system and not binary, octal or hexadecimal system. Imagine the days before the counting system was invented. How did people buy or sell things? Firstly, there was no money. Money was of no use if it could not be counted. Then, how did transactions take place? There was a system of exchanging goods which was called barter system. The cobbler would exchange a pair of shoes for a trouser. A farmer would trade in a bag of mangoes for a chair, and so on. Now I am going to tell you a probable reason why man needed a counting system. One day, the carpenter who gave a chair to the farmer was not satisfied with the quantity of mangoes he got in return. He started thinking of a way to overcome this problem in the future. After some hard thinking and after eliminating many other options, he decided to use his fingers to measure the quantity of mangoes. First, he closed all fingers before starting to count and called it nothing or naught. Then he took a mango from the bag and put aside. He opened a finger and called it 1. Then opened another finger for another mango and called it 2. It went on like that until he used up all the fingers to count 10 mangoes. Now he faced a new problem. How was he going to keep a count of more than 10 mangoes? He thought for a while and realized that if he closed all the fingers, he could start counting another 10. He found it easy to count the ones or the units, but it was difficult to remember how many tens he counted. After some serious thinking, he decided that he would keep a stick by the side of each 10 mangoes counted. So one stick and one open finger means 1 and 1, 11. Two sticks and 7 open fingers means 27. What would happen when he reached 10 sticks? Again, after some logical thinking, he took all 10 sticks aside, opened up another column by putting one stick to the left of the tens column and putting a circle in place of the tens column. Now it was one stick in the hundreds column, naught or zero in the tens column, and all fingers closed in both hands, another naught. It looked like this: 1, naught, naught, or 1, 0, 0, which was called 100. That explains the birth of the decimal counting system. Do you agree with
Binary system works. So let's get back to our lesson here. So these are called place value or column value. For each column, there is a value. And the values are determined like this. The first column is 10 to the power 0, which is 1. And that's called ones column. And the next one is 10 to the power 1, which is 10. And it's called tens column. And the third column is 0 10 to the power 2, which is 100. And that's called hundreds column. That's why it's a ones column, tens column, hundreds column. Those are the column values or place value. Now see the place value. Let's see how it happens. If we analyze the number 365, how do we get the values? This is 10 to the power 0, 10 to the power 1, 10 to the power 2, and the values are 100, 10, and 1 here. And you write the number 365. 3 here, 6 there, and 5. You multiply 100 times. 3 into 100, 300. 6 into 10 is 60. 5 into 1 is 5. And when you add up, you get 365. So what is the value of this 5? Now 5 is greater than 3, generally speaking, 5 is larger than 3. But 5 here in this column, the value of 5 is 5. 5 is 5 because the column value is 1. But here, the 3, which is lower than 5, but when 3 is in this column, it has a value of 300. So it's a place value that is very important when you analyze a number or the column value. Now let's get to binary numbers. Another system which is used by computers. The base 2. Then how many digits? 2. What are they? So here the values, the place value or the column values are, first one is 2 to the power 0, which is 1. Next 2 to the power 1, which is 2. 2 to the power 2 is 4. So these are the values: 1, 8, 16, 32. You have to know these by heart, memorize it, like 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, 8192, 60,000. Likewise, you have to double it, going doubling. What is a bit? A digit in the binary number system written using either of the symbols, either 0, 1, 0 and 1. Only those two symbols or the digits are used. And how the word came, bit, binary digit, binary digit, right? It's not the initials like normally you get, but this is from these two words came bit. And what is a byte? A group of 8 bits treated as a single unit. Like you have in the alphabet single characters, but when you make a group of single characters into a word, so similarly here, the 8 bits make up 1 byte. Now let's do a similar exercise like earlier to analyze this number. So similarly like this, you have to get all the column values to the power 0, 1, 2, up to 7. And then our number 101, 01, 01, no, sorry, 101, 1, then 01, and 101. So this is the same number which is written. Then we put the values. Where there is 1, you multiply 128. There is 0, so it's 0 into 64 is 0. 32, nothing here. 8, 4, nothing there, and 1. So when you add up all these values, you get 173. Now this one, all ones, 8 ones, convert into denary. So as usual, this 1 to 128, the sequence is there. And then you put all ones there, then 128, all the values are present. When you add up, you get 255. Then we come to hexadecimal, another system, which is the base is 16. Hex, as you know, is 16. Like pentagon, hexagon. That's it. That's how. 6. Hex is 16 and decimal is 10. So 6 and 10, 16. So the base is 16. Therefore, a rule 16 digits. Like a man with 15 fingers. And similarly, the earlier one binary and with 2 fingers. If you want to count, start count. Here what happens is 0 to 9. Okay, here's another question. Also, you will find that we'll be asking questions for you to answer because it's very important that you learn how to answer logically, right? So here it's a question for you. A big Indian and a little Indian are walking down a path. The little big Indian. Then who is the big Indian? So if you know the answer, post your answer in SLS or SLOS programmers. There's a WhatsApp group to see if your answer is correct. If you are not a member yet, please send an email to admin@srilankaonlineschool.com to join the group. This group is very useful where you can have a share with the other students your problem as well as answering others' questions. So try to be the answer and then get it going. This is the file that I'll be using for notes, like you want to show some example or something. Yes. So same way, now I'm going to ask another question. In this you have the digits. 0 is a digit, 1 is a digit, 2 is a digit. This is the decimal denary system. 3 is a digit, 5 is a digit, 7 is a digit, 8 is a digit. All these are digits, single digits. 9 is a digit, but 10. If you type 10 here, 10 is not a digit. I'm saying 10 is not a digit. Then what is it? What is 10? 10 is not a digit. This is a digit. 7 is a digit. 8 is a digit. 9 is a digit. But 10 is not a digit. Then what is it? Yeah, you can pause this video and then try to think of the answer. Then after a little while, if you can get the answer or if you cannot get the answer, then you will replay this and find the answer. The answer is 7 is a digit, 8 is a digit, 9 is a digit, 10 is not a digit, it is 2 digits. See how easy, but you never think like that. So we have to get used to thinking that in that pattern. So in this hexadecimal, what happens? 0 to 9 you can borrow from the denary system. But afterwards, can you use 10? Because also another thing, the highest digit is in this 15. How do you know? Or how do you determine that? Let's take everything easy. The unknown systems like the binary and the hexadecimal, octal, or any system, you can understand by comparing it to the known one. Known one is the denary system. What is the highest digit possible in denary? Listen carefully to the question. What is the highest digit? Or what is the highest value in one's column? The highest digit out of the 10 digits is 9. So 10 minus 1. The base minus 1. When you go to binary, the highest is 1. That is, base is 2. 2 minus 1. Therefore, hexadecimal, the base is 16. Then the highest digit is 15. 1 minus 16 minus 1. If you know these patterns, you don't have to calculate and waste time. You know that the exam, you can't use the calculator. Not only for examples, I am giving you shortcuts so that you can save time at the exam. But since 10 is not a digit, it's 2 digits, we had to invent digits, new digits. So we took A for 10, B for 11, C 12, D 13, E 14, and F 15. And the column values of base, no? Always is the base here at the beginning, column values, base to the power 0, base to the power, that is 10 to the power 0, 10 to the power 1. And in binary, base is 2, 2 to the power 0. So naturally, in hexadecimal, base is 16, so column values are 16 to the power. So 16 to the power 0 is 1, 16 to the power 1, 16 to the power 2 is 256. You'll have to improve your arithmetic, the calculation to 16 tables. Different systems. Binary. Base is 2. Anyway, any counting system, you start with 0. Next one is 1. We have reached the highest number here. In binary, if there are 2 fingers, we use 0 and 1, and we have finished the 2 fingers. Then we have to open up another finger. So close this finger, it becomes 0, and put a stick by the side, as you saw in the video, 1, 0. How do we connect this to the known one, denary? The denary, you go up from 0 up to the 9, the maximum possible in one digit, 9. Then we have to close the fingers all 10 fingers, and then open up another one, another column this side. Same thing happens here. You have finished the 2 fingers, close the 2 fingers again to make it 0, and then put a stick on this side, so 1, 0. Then again, 1, 1. When you add 1 to this, 1, 1. And the next one is, again, you add, starting from right side, you add 1. You count, that's from the right side. So 1 plus 1 is, what happened? You have reached the max. So you have to, again, close, and that means it's 0. And here, carry, no? You have to add 1 to this one. Carry. Then what happens? That 1 and 1 also becomes 0. 1, 0 rather. Where it reaches 1, the next number, when you add 1, it will become 1, 0. Here also, this carried from here goes to this, and 1 plus 1 is 1, 0. And another column, this 1 is carried to the other column. Right? Likewise, now again, what happens? 1, 0, 1. Like 100 plus 1 is 101. Of course, this is not 100. Just for comparison purposes, I said there are no numbers for binary. This is 100, and this is 101. Then what happens? Next number. 1, 1, 0. Have a good look and see whether you understand. Then 1, 1, 1. Then what happens? All three full. Then you have to open up another column. That is 1, 0, 0, 0. These three, like 9 after 999, it's 1000, something like that. 111 is like 999 in binary. Again, starting 1, 0, 0, 1, then 1, 0, 1, 0, 1, 0, 1, 1. See the pattern. Also, another pattern you have to notice is the first, the ones column, in this, the ones column is always 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. If this column is 1, the next column is 0. So that is also one way of checking whether your answer is correct. And also these don't change until the previous one changes. Until the previous one changes, this one will not change. So safely we can put this as 1. And the next one changes because the previous two change. So then that's it. Again, this. This 1 and 1 won't change. So you can easily put 1 and 1. This also doesn't change. Only this changes. Next one, since this first one changes, the second bit also changes, but the other two remain the same. 1, 0. Okay? 1, 1, 1, 1. Then what happens? All 4 to be zeros and another new column to be taken. Expert on this 1, 0, 0, 1. These two no change, but the next one changes because the previous two become 0 again. Only the first one changes. Now the first two will change. Again, the first one only changes. Then 3 columns. 3 ones change to 0. So the one before that also changes. Then only the first bit changes. 1, 1, 0, 0, 1. Then the second one also changes. 1, 0. Yeah. Again, the first bit only changes. Two bits change. 1, 1 becomes 0. So the third one also changes. Now again, the first bit. Now the second bit. And now again, only the first bit. And all become ones. Then you know what happens next? A new column and all those four. Yeah. There are 5 ones, 5 zeros. Is 6, 16. Or let's take base 8 first. Base 8 is what you call octal. 6, 8. Like octagon, octopus, octopus 8 tentacles, like that. Starting with 0 as usual and going up to 7, because base minus 1. 8 minus 1 is the highest digit. Once you reach the highest digit, you have to make it 0 and go to open up a new column there. Then you can go up to 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, again up to 1, 7 and finish. Then you have to make an add 1 to the next column, 2, 0. Are you following? You can't pause the video, replay, and then learn. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 7, then 1. 3, 0. Likewise, it goes on. 3, 1, 3, 2, 3, 3, 3, 5, 3, 6, and so on it goes. 3, 7, then 1. 4, 0. Okay. Then let's take to hexadecimal. As usual, you start with 0 and go up to 9. Borrowed from the denary system. Thereafter, you can't put 10 because we have not reached the highest. What's the highest number? 16 minus 1 is 15. So we learned earlier that A is used for 10 and B for 11, C for 12, D for 13, E for 14, and F for 15. So we have reached here in denary, the equivalent. We have reached the highest. Then what do? Close it. Close the 15 fingers and start again after putting one stick by the side, which looks 1, 0 and not 20, remember, not 10. And this is not 20. This is not 17. All these, you'll have to use the digit names, 1, 0, 1, 7, 2, 0. Same way here, 1, 0, not 10. Next one is 1, 1. 1, 2, 1, 3, 1, 6, 1, 7, 1, 8, 1, 9. Afterwards, what? 1, 8. Correct. Very good. 1A, 1B, 1C, 1D, 1, now what? Now what? Second time also we have reached the highest. Then you add 1, put another stick, that means 2, 0. Not 20, 2, 0. Right? So So the counting system. Okay. Let's have another one. Quadradecimal. What is that? I never heard. Can call anything. We can devise our own system. So quadra is 4. Quadra is 4 like penta. 4 and 10, 14. So the base is 14 and the highest digit is 13. So you go up to 13 like this. After 9, as usual, A, B, C, D. D is 13. So you have to stop at D and then close the 14 fingers, 0 and 1. So that is easier. 0. Again, go up to 1D. After 1D, 2, 0. So that is how that goes. All right. Now it's come to converting between binary and denary numbers. Denary to binary, divide by 2. You already know about this. The useful way to convert a denary value to its binary equivalent is the procedure of successive division by 2 with the remainder written down at each stage. The converted number is then given as the set of remainders in reverse order. That is from bottom up, not this way, but that way, bottom up. So this can be illustrated by the conversion of denary 246 to binary. Denary 246 to binary. Write 246 here, divide by 2. How much? 123. 246 divided by 2 is 123. Anything remaining? No, it goes exactly 246. So remainder is 0. Then you take this 123 here again and divide by 2. That goes 61 times 2 is 122. There is a remainder because this is 123. Remainder is 1. Divide 61 by 2. This, the answer here is taken here and divide 30. 2 times 30 is 60. There is remainder. Then 2 times 15 is 30. No remainder because exactly dividing. Then you get 15 here and divide. You get 7 and remainder 1. 7 divided by 2, 3 remainder 1. 3 divided by 2, 1 and remainder 1. And 1 divided by 2. There's no 2's for 1. So you put 0 here and 1 remainder. So the answer, if you take it this way, 4 ones will come first. 1, 2, 3, 4 ones. Then 0, 1, 1, 0. 0, 1, 1, 0. That is the answer. So now also you can pause the video and see whether you can calculate any, convert any denary number to binary. Then how do the reverse convert back to denary, a binary number back to denary? Take this 11001. First you write the column values. 2 to the power 0, it is 1. 2 to the power 1 is 2, 4, 8, 16. Then multiply as usual these values. 16 into 1, 8 into 1, 4 into 0 is 0. Here is a 0, there's 1. 16 plus 18 is 24. 24 plus 1 is 25. You have to be very quick like this. 16 plus 16, 24, and don't say 16 plus 8. When you count, a number, right? 15, 4, 32, 45, 62, 25, like that. When you count, how do you count? 5. 5 plus 4 is 9. 9 plus 2 is 11. 11, 5 is 16. 16 plus 2 is 18. 18 plus 5 is 20. That will take a long time. So what you must do is cut that plus this equals those things. You have to cut down. Cut down everything in your mind also. Just take this number 5 and you know that when 5 plus 4 is 9, don't say plus 5 plus 4 is 9. No, just say 5 here, 9, 11, 16, 18, 23. Then 2 is carried. You take this 2 plus 1. You don't say 2 plus 1. So you say 2, 3, 5, 8, 12, 18, 20. Okay, so that's the way you must do. So 16, 24, 25. Conversions for hexadecimal numbers. Denary to hexadecimal. Oh, divide by this. Here in the binary, denary to binary, we divided by 2, that is a base. So same way, hexadecimal, even if this book doesn't say, even if my note doesn't say 16, you should be able to conclude. You have to decide. You can come to that conclusion that, okay, this must be 16, I'm sure. That's the way. To progress, you learn. On your own, you can learn. So divide by 16 and remainders in reverse order. So I'm going to do it because you know the normal division. The remainders, you know it. So the other way around is hexadecimal to binary. Imagine 7BF. As usual, you have to put the column values like what we did earlier. The binary, we did column values 2 to the power. Here 16 to the power. For hexadecimal. So 16 to the power 0 is 1. 16 to the power 1 is 16. 16 to the power 2 is 256. And 7, BF. 7 here, B there, F there. 7 into 256, 1792. 16 into B is how much? 11. B is 11. The value, denary value. So 11 into 16, 176. You know that these are denary calculations. So we are doing, when you are converting, we are doing in denary. So 1 times 256 is denary calculation. So here also, you have to make this 11, the denary equivalent, and then multiply. Here it's 15. F is 15. So 15 into 1 is 15. And when you add up, you get this number. Converting between binary cuts like between binary, convert to something, and then convert to another. No, it's not that. Very easy. Going to hex, you just write the binary number here. If this is the binary number, take 4 bits apart from the right side, remember? From the right side. Because if you take from the left side, if there are more than 8, if there are 9 or 11, then this value will be different. But if you take from the right side, divide them into 4 bits each. Then if there is another bit here, doesn't matter, the value doesn't change. So this, the first 4 bits is value 0 here. No, sorry, the column values are 1, 2, 4, and 8. So the value of this one is 8. The value of this one is 4. So 8 plus 4 is 12. And 12 in hexadecimal is C. 1011 is, the value of this is 8. This is 2. This is 1. So 8 plus 2 plus 1 is 11. 11 in hexadecimal is B. So what is this group of 4 bits called? Group of 8 bits is called byte, you know that. So group of 4 bits is half a byte. And the name given to that is a nibble. Nibble. So one nibble needed to represent one hexadecimal digit. And hex to bin, the other way around. Reverse of it. If it is B9, what? B, the value of B is in denary, it's 11. So in binary, 8 plus 2 plus 1 is 11. This is how you write in binary. So that nibble is for B, 1011. And for 9, 8 plus 1 is 9. So that's the second nibble for the second digit. You don't say bits in hexadecimal. The C is not a bit, B is not a bit, they are digits. Your bit is binary digit. So only for binary, you can use the word bit. Then what do you use hexadecimal for? Usage of hexadecimal. A memory dump could be provided which has a hexadecimal representation of the content of some chosen part of the memory. That like if now, I'm not giving you how to get this because I'm not quite sure whether this is 100% safe. Is anyway the dump is given like this. The position or the situation in the memory, the condition of the memory at that time, if a program crashes or something, when the programmer wants, when you complain, the programmer will ask for a memory dump. What was there at that time? Then the programmer can go through these each address and the values. These are hexadecimal values, and then find out what happened, what was the cause of the error, and then you can correct. So for that, hexadecimal is used. Then choose also to represent MAC address. MAC address is a physical address which doesn't change. Even if you go abroad, take your PC abroad even, it will not change, unlike the IP address. IP address can change even at home from time to time. You will learn later about dynamic IP addresses and static IP addresses. But this is physical. It's given physical address. You can find out by on your computer, go to command prompt and issue this command IP config all. You will get this screen. So that is one. First one is memory dump. Second one is MAC address. Then to represent IPv6 addresses. IPv6, IPv4 only we are using now at the moment. Example is like 198.245.100.10. You may have seen IP addresses like this. These are the IPv4 address. Then for IPv6 address, the top one. You have 6 set of numbers using hexadecimal digits. Right? Sorry, 8, not 6, 8. 8 set of a set of numbers, set of 8 now, right? That's the format for IPv6 address. So for that also use hexadecimal. To create another use is to create colors in HTML web pages. This is a command you can use, one of the commands that you can use to show the colors. This is red. I will explain to you that how you can get it. Here is a this has a source of you can check the source code of any web page like this. Right mouse click on web source. Is this? I will show you a new one. How do you do a web page? Take a notepad or any text processing window, document. When it opens, you type your commands, HTML commands. HTML is hypertext markup language and they are tags. They are all marked like this. Markup, that's why it's called markup. And you mentioned that HTML is HTML. And every opening one should be closed like this with a slash in front. Then the body, which will show whatever on the screen that it shows will be this. To close. And in between, inside the body, whatever that you type. This is my first web page. You may have done web pages first, but I'm just doing this the general thing, or generally any programming language or any first thing you say hello world. No? Hello. I need BR or BR. There is no opening or closing. That just because you don't have to open and close. This is my first web page. If it is our first web page, otherwise you can say this is my 100th web page or something. Then you save it. You have to know, you have to remember where you save. I'll just put it desktop at the moment. And web page. That very important thing. Don't press enter until you press HTML. .html. This is very important. Otherwise, it will not be saved as a web page. This part, .html. So the name you can save it, and you check the here web page. Over, this is my first web page. Now let's do a little bit of change to show color. Learning now why where hexadecimal is used. So you can see I can give the background color of the whole web page by this body BG color equals it's a green. It is not hexadecimal. Without hexadecimal, I am giving a color by the name of the color, but that is limited. All right, so I'll save this and reload this page. Yeah, became green, and you can say yellow. The wrong spellings. Save and reload. There you are. Now, still we don't know how to use the hexadecimal part. So let's do it. Use the hash symbol. Then there are three colors RGB. RGB. For these two, you have to replace with hexadecimal values. And in hexadecimal values, you know that F is the highest digit, highest value for one digit. And there are two digits here, two hexadecimal digits. That means two nibbles and one byte or one byte. So here, if I give FF, that will be the max, no? Maximum for red. This is red. I am replacing red with the value. G for green, just put 00 and blue also 00. What will happen? Save it and reload. It became red. Now we do, let's give the green. So 00 for red, FF for green, F00 for blue. Save it, reload. Green. And finally, blue. FF for blue. Save, reload, blue. What if we mix up like this? Green and blue. Max. Cyan. Or cyan. And instead of that, red and blue. Save magenta or something color. Some color I can't remember. So likewise, you can combine. Not only FF, you can give values like 1, 8, A, D, 1 or D. Like that, you can give hexadecimal value. many, uh, many shades. In fact, you can get up to 16 million colors or shades because each one, this byte, there for red, there are 256 values. For green, there are 256 values because FF is 256. One byte, one byte has a value of total number of values of 256. So 256 into 256 into 256 will give you 16 million plus colors, right? That is another application where you create colors in HTML web pages. And another one, in charts that define character codes. Example is ASCII chart. We will be learning this later. ASCII character code that I told you briefly earlier, when you type A, it doesn't go as A into the computer, but it goes as a code. And the codes are given or all have come to an agreement called ASCII. ASCII chart. ASCII is the American Standard Code for Information Interchange. All the computers should follow this method. For example, A, capital A is denary 65. The binary value of denary 65 is given for capital A. Simple A, 97. So, how many usages? One is memory dump, called memory dump, MAC addresses, IPv6 addresses, create colors in HTML and to use in character codes. This task for you, convert each of the denary numbers 96, 215 and 374 into hexadecimal numbers. Convert each of the hexadecimal numbers V4, FF and 3A, 2C to denary numbers. Where do you submit them? I will show you. Here under information representation, task 1.01, activity 1.2, task 1.02. There's a whole lot of things to do. Well, you're doing the exam, not myself. So if you do this, I show you, but that is not the point. You have to do, don't miss a single one of them. I'm repeating, don't miss any of these things. You better do this. This you will see. A quiz will come like this. Convert the hexadecimal number FF into binary. You give the answer here, and then there are, in this case, there are 6 numbers, and you finish attempt. You click finish attempt. It will come like this. Here, of course, not yet answered, but when you answer, it will say answered, and either return to attempt or submit all and finish. Then again, you have to submit all and finish. Then it will give you the results. Yeah? 0, because all are wrong. This red is wrong, because I didn't answer it. And the correct answer is also given. So you can learn if there's a mistake, why is it wrong. Okay. I hope you will enjoy this, doing these quizzes. I know children like quizzes, just normal exercises. Right, back to the lesson. Yeah. Then, so here are the task 1.01, we have to do and submit and get the results yourself. 1.02, numbers and quantities. A number expressed in exponential notation. That is, like this, minus 3.6 into 10.8 or 4.2 into 10 to the power minus 9. This is minus 3.6 into 10 to the power 8. 10 to the power minus 9. Anything is okay. Using exponents, the value can be positive or negative, and the exponent can be positive or negative. You saw it here. Then Example, give 1,250,000 bytes in exponential notation. So what do? You bring this decimal point this way and make it smaller. Or here I have taken 3 places decimal. 1, 2, 3, and up to this point, 1,250 into 10 to the power 3. How is 10 to the power 3? Because for each zero, you multiply by 10 to the power 1. So here 3 zeros, 10 to the power 3. And if you take 1.250, that means another 3 you have brought here. So 10 to the power 6. And this is the best way to represent big numbers. One byte equals 8 bits. Now we are learning the decimal prefix and the binary prefix. You know that 1 byte equals 8 bits. After that, this is same in both. 1 byte equals 8 bits. After that, it changes, the prefix changes according to decimal and denary and binary. So here, this is the decimal prefix name, it's kilo. Symbol is K and the factor 10 to the power 3. And each step is 10 to the power 3. We are going down. That's why you get 10 to the power 3, 10 to the power 6, 9, 12. Each step is 10 to the power 3. So to go to mega, it is bytes, megabytes. 10 to the power 6 bytes. For kilo, 10 to the power 3 bytes, that is 1000. Mega is 1 million. Giga is 1 billion and tera is trillion. Right? Then that's a decimal prefix, a prefix to define the magnitude of a value. Examples are kilo, mega, giga, and tera, representing factors of 10 to the power 3, 6, 9, and 12 respectively. For the binary prefix, it's called kibi. The name is kibi, not kilo. Kibi and the symbol is Ki and the factor is 2 to the power 10. There we saw is that 10 to the power 3. Here is 2 to the power 10, which is 1024. And each step is 2 to the power 10. Here, going down this way, we have to multiply by 2 to the power 10. So kibi, you have 2 to the power 10 or 1024 bytes. For the maybe, 2 to the power 10 into 2 to the power 10 or 2024 into 1024. Okay. Then gibi is 2 to the power 30 and tebi is 2 to the power 40. The names are like this: kibi and gibi, right? Gi, maybe and tebi. So alternating every other one, ab. But the prefixes are always ai, the letter, second letter is I. Here the second letter, kibi and gibi is I, maybe and tebi is E. Pronunciation also, kibi bytes, maybe byte, kibi, tebi, tebi. But the symbol always I. Remember that. So the binary prefix, a prefix to define the magnitude of a value. Examples are kibi, maybe, gibi, and tebi, representing factors of 2 to the power 10, 20, 30, and 40 respectively. Magnitude is the size. Exponent is a number written above and to the right of the base. That is this. 10 is the exponent and this is the base, 2 to the power 10. A number is best represented with either one denary digit or two denary digits before the decimal point. We saw it earlier, like 2.4 or max is 2.57. 24.2. If it is 24.2, that is two denary digits in front of the decimal point. Or else, even better, just one digit in front of the decimal. So what is the question? How many files of size 2.4 MB bytes could be stored, maybe bytes could be stored on a 4 GB byte memory stick? So have a good look at this how it happens. First of all, you convert the gigabyte, the space, the available space into the file size that you need. You have to bring those two. These are different units, megabytes and gigabytes. You have to bring them into a common one. So rather than taking megabytes to gigabytes, you always take the gigabytes to megabytes. Then it's easier. So convert 4 gigabytes to megabytes is 4 into 1024. Because here you saw each step is 1024 or 2 to the power. Bringing gigabytes to megabytes, you have to multiply by 1024. So if there are 4 gigabytes, then 4 into 1024 to find capacity available. So that will give you the memory stick full capacity. Then divide the capacity by the file size. So this is it. 4 into 1024 divided by 2.4 is the. Remember, you don't have to give the final answers like this. You can give like this. That's also given, marks given for this. Because you're not supposed to take the calculator to the exam hall. You can't take calculator. So because of that, this is accepted. Marks given like this. Then this is for you. How many megabytes are there in 2 gigabytes? See whether you can do it. Yeah, so it's easy. How do you do? 2 gigabyte. 1 gigabyte is how many megabyte? Let's look at the chart. 1 gigabyte. 1 gigabyte is 1024. The step is 1024. Each step 1024 megabytes. So if it is 2 gigabytes, 2 into 1024. So the answer here is 2 into 1024 megabytes. Then we come to what they call internal coding of numbers. Binary addition also, it's given here, like 0 plus 0 is the rules. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 equals, is this 10? No, it's 1, 0. And I have given for easy reference, denary, it's 2. 2 in denary. Here, 1, 0. And also, this will be useful later on in calculation. If 1 plus 1 is 1, 0, then 1, 0 minus 1 should be 1, no? You take this 1 into this side. This side will become 10 minus 1. That's not 10, 1, 0. You take this one here, 1, 0 minus 1 equals, this is remaining this side, 1. That will be useful. Then 1 plus 1 plus 1 equals 1, 1. In denary, it's 3. So here is an example. 1, 0, 1, 1, 0, 0 is 44. How do you know? 1, 2, 4, 8, 16, 32. So we calculate like this, 1, 2, 4, 8, 16, 32. Then go backwards. 32 plus, there's nothing here in the 32, 16 column. So it's 8. 32 plus 8 is 40. 40 plus 4 is 44. And this is 1, 2, 4. 4 plus 1 is 5. And when you add up, you should get 49. Let's see whether you get 49. 1, 2, 4, 8, 16, 32. 32 plus 16 is 48. 48 plus 1 is 49. Right. And how do we do it? Now only I'm showing it. 0 plus 1 is 1. 0 plus 0 is 0. 1 plus 1 is, remember, 1 plus 1 is 1, 0. So you put 0 here and carry 1. That 1 is written here. Carry 1 to the next column. That 1 and this 1 is again 1, 0. So you put 0 here, then carry carry to the other column. So there's nothing to add. So that carry will come here. And here no change. 1 plus 0 is 1. And we, in advance, we knew that this answer is correct, 49. In the binary, these are the rules. 0 minus 0 equals 0. 1 minus 0 equals 1. 0 minus 1 is minus 1, or the normal way, borrow from next column. That is like 12 minus 7. How do you do? 2 minus 7 first. 2 minus 7. If you can't, here, so if you want to deduct, subtract 12 minus 7, 12, you write 12 there, minus 7 here. What do we do? 2 minus 7, no? 2 minus 7, you can't, no? You can't subtract 7 from 2. Then what do? You borrow this 1 to this side. Then this will not become 3. You are not just adding 1 here. You are getting the full column value. That is 10. So 10 plus 2 is 12. Then you subtract 7 from 12. Same way here. This is also useful to remember. When you borrow, it doesn't become 1, it becomes 1, 0. You will know, you will see it in this way. When you do this subtraction, this is the number, this is the number to subtract. 0 minus 1, we can't, no? We can't deduct 1 from 0. So you borrow this 1 to this. From the next column, you borrow 1. What happens here? That's what I was explaining. It won't become 1. It will be 1, 0. Because the column value here have to be taken into account. So second column, like, we add a column like, so 1, 0, 1, 0. This becomes 1, 0. And 1, 0 minus 1 is 1. That is what I showed you. 1, 0 minus 1 is 1. Then how much is here? It's 0 there. Right? It's 0 there. So 0 minus 1, again you have to borrow. Since there is no 1 here, you have to borrow 1 from there. So when you borrow 1 from here, this becomes 1, 0. This becomes 0 and this becomes 1, 0. Then what happens? From here, you borrow 1 to this place, it becomes 1, 0, and this becomes 1. From 1, 0 minus 1 is 1, same as this. 1, 0 minus 1 is 1. Then here, there is 1 remaining, no? From 1, 0, this became 1, 0, and you took 1. So here remaining 1. 1 minus 1 is 0. And here is nothing because we borrowed this initially. So 0 minus 0 is 0. Then there is no change. Here, 1 minus 1 is 0. Let's see whether we can do an example here. Binary subtraction. Okay. This is 170. How is it? 1, 2, 4, 8, 16, 32, 64, 128. So 128 plus, this is not 60, 64 is 0, this is 32. You can add. 164 plus 32 is 196. 196 plus 8 is 204. Sorry, see, 1, 2, 4, 8, 16, 32, 64, 128. 128 plus this is 32. 128 plus 32 is 160. 132 plus 128 plus 32 is 160. So you must be very quick in calculation, mental calculation. For that, uh, I have given a thing for a quiz for you. I'll show it in a minute. Suppose here, if you start from the top, you will have this one, start the engine. Start a quiz. Duration, 10 minutes. There is a total of 100 questions, times tables. So you have to be very thorough. 100 questions are there and the time is running. 6 into 6 is how much? Then 10 into 5 at random, it will come. Every time you do, it will be different questions all the time. So you do that and automatically you will be graded. All right. Here for the calculation. So that's why I told you that you have to be very fluent in the arithmetic. So 128 plus 64, not 64, 32. 128 plus 32 is 160. 160 plus 868 and 270. So that's 170 and minus how much? Minus how much? 1, 2, 4, 8. This is 128 plus 3 is 131. Okay. Then as you did this, then you get the answers how much? 1, 2, 4, 8, 16, 32. So 170 minus 31. Let's see. See what our, yeah, see 20 minus, this is a different one, 135. 1, 2, 4, 8, 16, 32, 128. 128 plus, this is 7 actually. 1, 4 plus 2 plus 1 is 7. That also you must be very thorough. 1, 1, 1 is 7. So 128 plus 7 is 135. And you should get 35 as the answer. Let's see whether you get it. And the way to do it is, first of all, these are the two numbers for the calculation. These are the two numbers involved. What is in red? That is the working in between steps for you to understand. So first you ignore this. Don't look at this. 0, this 0 minus 1. You can't deduct 1 from 0. You can't deduct 1 from 0. So then what do? You borrow, no? You borrow from the other one. This column, next column, you borrow 1. What happens to this 0? It becomes 1, 0. Remember, I told you, this becomes 1, 0. From 1, 0, you can deduct 1, and the answer is 1. Then here, what happens? Here, this was 0, no? Earlier, borrow this 1, it goes to that side and makes it 1, 0. Here, it becomes 0. So what do you do then? You can't. This is 0. You can't deduct 1 from 0. Again, you have the same problem. So try to borrow from here, nothing. Try to borrow from there, yes. So this 1, when you take it here, it becomes 1, 0. This 1, when it comes here, it becomes 1, 0. And from here, you take 1. This side, okay? This will be 1, and this will become 0 will become 1, 0 with this 1 here. Then 1, 0 minus 1 is 1. And here we are left with 1 here. 1 minus 1 is 0. Here, 0. 0 minus 0 is 0. 0 minus 0 is 0. 1 minus 0 is 1. 0 minus 0 is 0. 1 minus 1 is 0. And how much is it? 1, 2, 4, 8, 16, 32. This is 32. 32 plus 2 is 34, plus 1 is 35. So that's correct. So that's the way you subtract. And how you borrow is, that's the way. Now, another small section, coding for integers. How are integers represented in the computer? With 1 byte, if you want only positive numbers only, then you can use all 8 bits. Use all 8 bits and go up to 255 is the highest number. So with 0, altogether 256 numbers you can have. If you have 2 bytes, you can go from 0 to 65,535. You can calculate and see. Uh, with 1 byte, if you need negative and positive only, I mean, if you want what you call the sign, if you need to know whether it's negative or positive, because here there is no sign in binary. In binary, you don't have any sign bits, only zeros and one. That's all. So we had to use one of them as a sign. So we use the MSB, the most significant bit, as a sign. And if it is 1, it's negative. If it is 0, it's positive. The 8th bit, the sign. And you have only 7 bits for the value. So therefore, 127. If all are ones, it's 127. So this is minus. No? First one is 1 means the other 7 are ones. That means minus 127. 2. 0 means plus here, plus 127. Minus 127 to plus 127. So I will show you a shortcut now to calculate values of this. All at once, can you tell the value of this? You can't, no? You be adding 1, 2, 4 and all that. I'll show you a shortcut for that. We will save you a lot of time. Look at this. If you have 1, just 1, the value is 1, right? You have 2 ones, this and this. That means 2 plus 1 is 3. Then if you have 3 bits, 1, 2, 4, the value of this bit is 4. 4 plus 2 plus 1 is 7. And this 8, 4, 2, 1, 15. If it is 16, this becomes 31. If it's 32, this becomes 63. So likewise it goes. What is the formula? There is a pattern here. You have to recognize patterns always. Then that is what you call learning. You can learn on your own a lot of things if you recognize patterns. You can recognize. So here is a pattern. 2 plus 1 is the answer here. Here 4 plus 3 is the answer, 7. 8 plus 7 is 15. That is the earlier one here. 8 plus 7. 16 plus 15, the earlier number, 31. 32 plus 31, that's 63. So how do you, now what is that? Now you can't, if you have like this, it's okay. But all of a sudden, if you say 8 ones or 12 ones, then you can't be doing all this. No? So the formula is you add you get the value of this and add minus 1. 1 less than that. That means 2 plus 2 minus 1. And here 4. 4 plus 4 minus 1, that is 3. That is this here. And this is 8 plus 7 means 8 plus 8 minus 1. This is 16 plus 16 minus 1. 32 plus 32 minus 1 is 31. So then what we have here, we want to know the value of this. How do you do? Just count on 1, 2, 4, 8, 16, 32, 64, 128. 128 plus how much? 1 less than 128. That's 127. That is 128 plus 127 is 255. This one, this P2 don't count. So let's take this 1, 2, 4, 8, 16, 32, 64. 64 plus how much? 63. That's 127. So thereafter, you don't calculate. If you have something like this, don't do any calculation, just use that method. And if you want 32, what do you do? 1, 2, 4, 8, 16, 32, and all the others are zeros. So same way 64, one more zero than this. And if it is 65, what? Take 64 and add one there, this side. Okay. And how much is this? 1, 2, 4, 8, 16, 32, 64. 64 plus, imagine that this is also 1. This is also 1. You use that rule. 64 plus 63 is 127, but this is not 1. So you have to reduce 1, 126. All right. One more thing to remember is this. 2 ones is 3 in denary. 3 ones is 7. 4 ones is 15. 5 is 31. Like that. You have to remember these things. 15, very essential, very important to remember. 4 ones is 15. Then we are going into a bit more complicated section. 2's complement for signed integers. Remember, this is very important. 2's complement is only for negative numbers. Very important to remember. Remember these two colors also. You will find that I will prove that you have forgotten this in a little while. So how do you do? The first step is 1's complement. You take a number and turn it to 1's complement before turning it to 2's complement. How you do it is each binary digit is individually subtracted from 1. Complement means the opposite. So here, individual each bit to be reduced from 1. So you put all ones on top. This is the number to be converted. So you deduct this from 1, 1, 1, 1, 1. So 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. So it goes on. What happens? What is the result? This number has got inverted. The opposite of this. All the ones have become zeros and the zeros have become ones. Then what happens? 2's complement is you add 1 to 1's complement. So this is the answer here. This one is taken there and added 1. 1 plus 1 is 1, 0. 0 and 1 carried. You put 0 here and 1 is carried. And afterwards, the others invert. I mean, they're not, sorry, others, nothing. No change. You just add 1. 1 plus 1 is 1, 0. So 1 is carried and 1, 0. The others, same. You just put it. This is the 2's complement of this number. This is the 2's complement of this number. All right. So then we go on. This is the definition. 1's complement, the binary number obtained by subtracting each digit in a binary number from 1. So the shortcut is what? Just invert it. Any number, if you want to convert to 1's complement, don't go to do this long cut. 1, 1, 1, 1 and all that. This is only for the method, how to learn. What you must do is just invert it. This became this 1's complement just by inverting all the digits. The 2's complement, but of course, if you are asked to write what is 1's complement, then you have to write this definition. Binary number obtained by subtracting each digit in a binary number from 1. You remember the shortcut, but remember this also to write if you are asked to write the definition. Then 2's complement, the 1's complement of a binary number plus 1. So here are some questions. What is the ones complement of this number? Just invert, no? The two ones will become 0, 0. The two zeros will become 1, 1. 1, 0, 1, 0 will be 0, 1, 0, 1. What is the two's complement of this number? So first, you do the conversion, like the inversion. 0, this one will become 0. And how many zeros? 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 ones. And this 1, 0 will become 0, 1. Add 1. So this is the two's complement of this number. What is the two's complement of denary positive 100? So first you convert denary to 100. Denary 100 to binary. That is this. Let's see whether it's correct. 1, 2, 4, 8, 16, 32, 64. Whenever you get a number like this, always check it whether it's correct. Then your arithmetic will improve. So 1, 2, 4, 8, 16, 32, 64. 64 plus 32 is 96. 96 plus 4 is 100. So that's correct. Then add a 0 in front of this binary value. After converting this into binary, add a 0 here. That's all. Why? What about the ones complement and all that? If you know the answer, you're good, memory is good. Otherwise, I told you I'll remember these two colors also, and I'll prove that you forget this. Only for negative numbers. So you don't do any conversions for positive 100. Just the binary conversion and adding a 0 in front. What is the two's complement of denary negative 78? Convert 78 to binary, disregarding the minus sign. Just convert 78. So it is correct. 1, 2, 4, 8, 16, 32, 64. 64 plus 8 is 72, 76, 78. Correct. 78. Then what? Add a 0 in front. We'll put a 0 in front of this number. Convert this to its two's complement. So this is the inversion. 1, 0, all the whole thing is got inverted here. That is one's complement. Then you add 1. 1 plus 1 is 1, 0. 1 carried, that is here, 0, 0. Then no change, all these things. That is the answer to that. Whose complement of minus negative 78. Then what happened? Another one. Here. Convert 2's complement positive binary number to denary. Now it's the other way around. The number given here is already converted. It's a 2's complement positive binary number. Convert it to denary. Right. Ignore the leading 0. Ignore the leading 0. Right? That is positive. Then now convert to denary. Convert to denary. Right? So then 64, 32, 8, 4, and 1. So when you add up, you get the total. 64 and 32 is 96, 96, 104, 108, and 109. That is 109. Positive. Huh? Positive. Then convert 2's complement negative binary number. There's 1 in front, a negative binary number to denary. So convert to denary. How? This is the difference. This last one is minus. The most significant bit is minus 128. All right. So the number is 3 ones, 1, 1, 1, then 0, 1, 1, 0, 1. 0, 1, 1, 0, 1. And you convert. This is minus 120, is 64, 32, nothing there, 0, 8, 4, and 1. 200, minus 128 plus 64 plus 32 plus 8 plus 4 plus 1, that is minus 128 plus 109, which is minus 19. So the answer to this is minus 19. Okay. Then this is interesting. Representation of signed integers. Signed denary number to be represented. 7, 1, 0, 1, minus 0, minus 1, minus 7, minus 8. Sign and magnitude representation. Sign and magnitude representation is the first bit for the sign, and the rest is for the size or the value of the number. So if this is 0, that means positive, and 7 is 1, 1, 1. I told you, remember, 4 plus 2 plus 1, 1, 1, 1 is 7. I'll come to that later, use complement. First we'll do this column. So 1 is 0 for positive and 1. 0, again, 0 positive and 0. Minus 0 is 1, that is for the sign, the first one. This one means negative, 0. This one is negative and 1, so that is minus 1. Minus 7 is this negative, and 1, 1, 1 is 7. Minus 8 is not represented. Why is that? Because if you put this as negative, well, and then with 3 digits, you can't have 8. You need another bit for 8, no? 1, 0, 0, 0. That is why with 4 bits, it's not given. But of course, you can give, then you need another bit. But we are handling only 4 bits here. Then the 2's complement representation, the same thing. Why is that? Because that green and purple, that rule, no 2's complement conversion for positive numbers. So the first 3 numbers are the same. 0, 0, 0, 1, 0, 0, 0, 0. And minus 0 is not represented. Same problem there. Because I'll tell you how this is done. Here is minus 128. Sorry, minus 1, 2, 4, 8. Minus 8. The fourth digit is minus 8. Next one is plus 4. Next one is plus 2. Right. So a total of how much? Well, this is minus 8. This is plus 4 plus 2 or plus 1 is 7 here. 1, 1, 1 is 7. So 7 minus 8 is minus 1. See, minus 1 here. Right. Let's take another one. This is minus 8. Then 0, 0 plus 1. No values for these two. Only this has a value of 1. So that means that is minus 7. No? Here is minus 7. That's the value needed. So minus 8 is this. Minus 8, and the others are zeros. That is how it's your turn. Pause the video. Pause the video now and try to fill this up. Try to fill this up, and then you replay the video, and you can check whether these answers, your answers are correct. You can have any number, like, if it is 4 not enough, I will use the minimum number required. There is task 1.03. Convert the two's complement number 1011 to the denary equivalent. Then do the same for 111011 and convince yourself that you get the same value. What does that mean? We'll take these two numbers in the worksheet and try 1011. Right? 1011. It's a question. Convert the two's complement number. This is already two's complement to the denary equivalent. So, how do you do it? Take this is equal to -8 plus 2 plus 1, which is equal to how much? -8 plus 2 plus 1, 5. -5. -5. Then you asked to do this three ones. 111, 011. 111, 011. Convert that also and see. That's also negative. So minus how much? 1, 2, 4, 8, 16, 32. Minus 32 plus this is 16 plus 8 plus 2 plus 1. 2 plus 1. This is 0 here. So we are not adding 4. How much? Well, minus 32 plus, you add up these things. 16 plus 8 is 24, 24, 26, and 27. Which is how much? Minus 32 plus 27 is minus 5. So this answer is the same, no? Same as this. So what is the meaning? You can add any number of ones in front. Two's complement, remember, only. Otherwise, the normal binary, it will change the value. For two's complement, you can, negative ones, you can add any number of ones in front. Zeros. Usually we say no, add zeros in front and no value change. Yeah. That is because this one will become higher and the others also will offset that. See? Here -8 plus 2 plus 1. This 2 plus 1 remains the same. But all these ones make up to this one. So the final answer will be the same. And so is it, and convince yourself that you get the same value. So binary arithmetic, you know the additions and the subtraction, the rules. Now what happens here? You add this 1011 and 1 plus 1110. What happens? 1 plus 0 is 1. 1 plus 1 is 1, 0. 0 plus 1 is, sorry, 1 plus 0 is 1. 1 plus 1 is 1, 0. 1 is carried. That one and this one is 1, 0. 1 is carried. 1 plus 1 is 1, 0. Plus 1 is 1, 1. You put 1 here and then 1 carried. But we have a 4-bit register. Imagine that we are using a memory location which has only 4 bits we are using. Then what happens to this? This is called the overflow error. If binary values were limited to being stored in a nibble, 4 bits is nibble, excuse me, the result of the addition would be incorrectly stored as 1001. Because this is lost, no? Lost. There's no place to keep it. Like spelling 250, like pouring 250 milliliters of milk into a mug, which is only 200 milliliters. What happens? That 50 will overflow. That will be lost. The what will remain is only 200 milliliters. So here, incorrectly stored as 1001. The answer should be, now this is 11 and this is uh, 13. Sorry, 14. 8 plus 4 is 12, 12 plus 2 is 14. This is 14 and this is 11, should be 25. 11 plus 14, 25. But what is the answer? 1009 is 9. 8 plus 1 is 9. This is an example of an overflow. The value produced is too large to be stored. There was an exam question like this, so remember this, overflow. The condition when the result of a calculation is too large to fit into the number of bits defined for storing. Remember that? That's overflow. In that question, they had asked something like that for you to do the calculation and then comment on it, comment on the answer. So the answer is, what is the error it asks? What is the error called? The error is overflow error. And also you can say that the given bits, number of bits is not enough to store the answer. When the value in a computer system are stored in 2's complement form, this problem has a characteristic behavior. In the following addition, where plus 63 is added to plus 63, there is no problem. The answer is correctly obtained as plus 126. That is this. Okay? Now let's use our shortcut method to calculate the value of this. 1, 2, 4, 8, 16, 32. 32 plus how much? 1 less than 32, 31. So that will give you 63. This is also 63. And this one, 1, 2, 4, 8, 16, 32, 64. If all were ones, if this was also 100 and 64 plus 63 is 127. But since this is not 1, you reduce 1, this is 126. So that's answer is correct. It saves a lot of time to remember those methods. However, if the binary for plus 96 is added to plus 96, the result is as follows. So then 63 and 63, there was no problem. But this one, what happens? Is this 96? 1, 2, 4, 8, 16, 32, 64. 64 plus 32 is 96. Yeah. So when you add up all zeros, and here 1 plus 1 is 1, 0, 1 carried, 1 plus 1 is 1 carried. That will come here. What happened? There is no overflow, no? The overflow means that the answer has a leading 1, which causes a computer system to interpret the answer as a negative number. So here, what happens is 1, 2, 3, 4, 5, 6, 7, 8. The 8 bits, nothing lost. But where this should be plus 96 is 192, be 192. But what does this give? This is negative. 1, 2, 4, 8, 16, 32, 64. Negative 64 is the answer. So that's all wrong. A similar problem can occur when two negative values are added. For example, the addition of minus 96 to the same value results in the following. So that happens. What happens? Here, the overflow that this time, this is extra. This time there has been a carry when the most significant bits were added, and the result obtained is a positive number. So because of that, the answer became positive. So that's also wrong. Clearly, we need the processor to detect overflow and output an error message. There is a discussion of how a processor can detect overflow in chapter 6. So later on, we'll be learning those. Then the subtraction, again, this is like a reminder I have given this. And subtract binary equivalent of denary 11 from the binary equivalent of denary 14. What do you do? Is 14 minus 11. So it should be 3. That is okay. When you do that thing, normal, nothing happens. But Subtract the binary equivalent of binary 111 from the binary equivalent of 141. So this is also okay. 141 minus 111 is 30. So is this 30? 1, 2, 4, 8, 16. 16 plus 8, 24 plus 4, 28 plus 2 is 30. Yeah, that's correct. Then task 1.04 for you. Using a byte to represent each value, carry out the subtraction of denary 35 from denary 67 using binary arithmetic with 2's complement representation. 67 minus 35 equals 32. Our normal denary arithmetic. Here, what do? We need to overcome this carries and overflows and all that, right? Whatever the negative number, you convert to 2's complement and then add. No subtracting. So first of all, 67 plus 67 is this. 1, 2, 4, 8, 16, 32, 64. 64 plus 3 is 67. Then this is 35. What do you do? 1, 2, 4, 8, 16, 32. 32 plus 3 is 35. Remember the what do you call the 1's complement is inversion. The opposite of this is written here. Then add 1. Add 1 is this. So when you add, what happens is you will get this answer. And then this is brought here again to add up. No subtraction, you just add. And then you get this. There is a carry, there is an overflow, but you don't have to worry. Look at this, 1, 2, 4, 8, 16, 32. So it's correct, no? Plus 67 minus 35 is plus 32. So that's correct. The other way around, 35 minus 67 is minus 32. See whether that also becomes correct. So here is 35 and here is minus 67. Then we have to invert it. 1, 0, 1. All these big digits are inverted. Then you add 1. Then you get this number. And add up this. Bring this again. Add. You get this. Right? Get this number. And this is 128. Remember? For the negative numbers, this is 128. And all these positive ones, you get minus 32. Right. So that is correct. So you don't have to worry about these carries and overflows and all that. Changing the sign and all that. No need to worry if you use 2's complement. That is the reason. If you're wondering why this 2's complement, what's the use? This is the use of 2's complement. Then you have binary coded decimal. Way of coding digital displays and all that. 1 nibble for 1 binary digit. And only nibble is 4 bits. So 000 to 10011 are used. 1010 to 111 do not have any meaning. Why is that? Because single digit in denary, you can go only up to 9. So this is it, 0 to 9. And these have no meaning. You won't use those in BCD. Binary coded decimal, storage of a binary value representing 1 denary digit in a nibble. Storage of a binary value representing 1 denary digit in a nibble. And packed BCD is when 2 BCD nibbles are stored in 1 byte. So take this 8503. 8 is this. So only 1 nibble is used. Only 1 nibble is used. This is blank, this is empty or 0. Then the next one is 5. So this is 5. This is 0. And the last digit 3 is this. And packed is 2 BCD digits per byte. So in 1 byte, you put this as well as that. And the other byte, these 2 nibbles. Examples are calculator screen, the digital displays, and digital time displays. Those are the ones, BCD. And BCD arithmetic, there is a problem. If you add 0.26 to 0.85 should be 1.11. So how do you represent 0.26? 0.26. This is 1 byte for this 0, the whole number, integer part. This is a decimal number, and 26 is this nibble is 2. Remember, one nibble for one digit, digit, BCD. So, and this is 6. And 0.85, 0 point, this is 8, this is 5. And when you add up, what happens? When you add up, you get this. This table, you get 1, 0, and the value in denary, 10. And this is 11. As if like it's 0 or dot 1011. But that is wrong. You should get 1.11. And see the correction. How you do the correction? You add, you can read this. This note is uploaded, so you can always read this a number of times and video short. Otherwise, it will be very long. So this is a correction. The correction is 0, 1, 1, 0. You add it. Then what happens is 1 is carried. 1 plus 0 is 1. 1 plus 1 is 1, 0. 1 carried. 1 plus 1 is 1, 0. 1 carried. 1 plus 1 is 1, 0. 1 carried. Then it goes to the next table. We are not adding yet. We are adding that one, the next step, plus the correction. So 0, 1, 1, 0 plus 1 is this. When you add up, again you get a carry. Where do you keep it? You take it to this one, the next byte. In that case, 1 plus 1.11. So that is corrected. That is a correction. And now we can stop, because this is like a different kind of thing. Not many numbers coming into action. So after this, you try to master and try to do all the tasks and improve your knowledge. Hope you will enjoy this and do all the homework and improve. See you in the next video. Bye.